All right, can you see that?
Yes, I can see your screen and I can hear you clearly.
Yeah. All right. Hello, everyone. My name's Luke Slama. I'm a medical physicist at Charles Gairdner Hospital in Western Australia. I'm no longer a registrar. When I sent that email, I think I was a registrar, but I just finished my certification recently. So about 3 weeks ago. So now I'm a qualified medical physicist. Yeah, so I'm going to present on IMRT, VMAT, and IGRT, based on techniques and quality assurance based on Khan's The Physics of Radiotherapy, chapters 20
Sorry
and
to interrupt you,
26.
Luke. Your screen is frozen. I think it's not moving.
Sorry, can you see the mouse moving? No?
I can't see.
Let me just...
Yeah, it's now. It's now. I can see now.
Hold on, let me just go new share. All good?
Yeah. Now it's
Yeah.
All
right. So disclosure statement. I declare do not have any financial relationship with proprietary entries. Producing, marketing, reselling, or distributing healthcare goods or services consumed or used by patients in the past 24 months. So an overview of my presentation. I'm going to be presenting on IMRT and VMAT. So what is IMRT? Different models of MLC, methods of IMRT delivery, commissioning of MLCs and IMRT, QA of MLCs and IMRT, patient-specific QA, and then I'll be talking about IGRT. So different types of IGRT systems, respiratory motion management, adaptive radiotherapy, and then QA of IGRT systems. IMRT, intensely modulated radiation therapy, refers to a radiation therapy technique in which a non-uniform fluence is delivered to the patient to optimize the composite dose distribution in order to improve conformation of the dose to the planning target volume, or PTV, and minimizing dose to the organs at risk, or OIR. So an example of two fields. So this is a traditional 3D conformal treatment where you shape the field with the MLCs and you deliver a flat uniform field of radiation dose. And then on the right, you see a typical IMRT field where you modulate the dose in order to deliver regions of high and low dose in order to improve conformality to the planning target volume and reduce dose to the organs at risk. So in order to deliver IMRT, you require a treatment planning computer that is capable of calculating non-uniform fluence maps. So this is an example of a non-uniform fluence map, and a system of delivering the non-uniform fluence to the patient. So first I'll quickly go through some MLC models. So there are multiple different MLC models. The MLC is a set of thin tungsten leaf pairs used to shape the dose distribution. And they are also used to provide intensity modulation in IMRT and VMAT treatments. So there's example of some models of MLCs. You have the Elector model, the Siemens model, and the Varian model. They have different head designs. So for the Elector, the MLCs are above the jaws, and same with the Siemens. So Siemens are below the jaws, and then the Varian are below the jaws as well. And then this is a typical design of a MLC leaf. They have a tongue and a groove. So the tongue and groove design is designed to reduce the leakage between the leaves to an average of 2% and a maximum of 5% is design criteria that they attempt to achieve. And then it also has this rounded leaf tip design. And the idea of this is to, because the MLCs move straight in and out in the field, if you have a flat MLC leaf tip, you have a different penumbra at different field size. And the rounded MLC leaf tip essentially just increases the transmission through the leaves in order to achieve an equal penumbral width at different field sizes. And this makes modeling a lot easier in the treatment planning system. Different methods of IMRT. So there are multiple different methods of IMRT delivery. So with linear accelerators, you have segmental MLC delivery, or most often called step and shoot delivery. You have dynamic MLC delivery, sometimes called sliding window MLC, and then volumetric modulated arc therapy, or VMAT treatments, and then tomotherapy as well, which I'm not covering in this presentation, is another method of IMRT delivery. So first, step and shoot IMRT. So step and shoot is also known as segmental MLC. Each field is designed into a series of subfields of uniform intensity. So for example, This is a breast field. So you have 4, and this is a very basic step and shoot IMRT field where you have 4 segments, each of uniform intensity. And if you deliver this, you get a dose distribution similar to this, effluent similar to that. So when you deliver the fields, they're delivered in a stack arrangement. So the machine will deliver this one first, move the MLCs, deliver this one, move the MLCs, deliver this one, and then this one, all together in one delivery, and have a series of beam holds between those fields. Yeah, so it's switched off between subfields while the MLCs move, and as such, there is no moving parts while the beam is on. So the advantages of this is that there are no moving parts while the radiation is delivered. Therefore, there is less chance of MLC failure, and this will then require less maintenance requirements of your MLCs. It's a less complicated treatment than dynamic MLC, and therefore you can actually produce it, use forward planning and inverse planning. So forward planning, a typical field-in-field treatment technique for a breast treatment is forward planned. Portal verification is simple. It is easy to resume an interrupted treatment because there's no moving parts. It's easy for the MLCs to pick up back where they were last positioned. And because there's no motion of parts during the treatment, the MLC speed and acceleration does not impact the dosimetry of the patient. Disadvantages is that some accelerators do show instability between switching machine on and off constantly over short periods of time. And especially if you have a huge number of segments, sometimes you can get treatments up to 10 segments for very complicated treatments. You can get a lot longer treatment time compared to other MLC-based treatments, such as dynamic MLC and VMAT treatments. So the second treatment technique is dynamic MLC. In dynamic MLC, the leaf pairs are moving simultaneously and unidirectional. So the dose is modulated by modifying the MLC leaf speeds and dose rate. And then the optimal solution is to build up effluents to move one leaf at the maximum speed, and then the other leaf used to modulate the dose. So if the fluence is increasing, the leading leaf should be moving at the maximum speed, and the trailing leaf should be providing modulation, and the opposite is true if the fluence is decreasing. So this is an example of a DMLC field. So you see they start on the left, and all the MLCs are moving from the left to right, opening and then slowly closing as we deliver the field. And you see they're a bit slower at this end because we're delivering more radiation towards this end of the field. And this is the same fluence map as the previous step and shoot field, but this is just a different method of delivering effluents using a dynamic MLC method. The advantages of using a dynamic MLC is that it's a quicker treatment time than step and shoot, and you can produce more highly modulated treatment fields. So you aren't limited to just a few different intensity levels in your fluence. You can actually have a more smooth fluence distribution. There are many disadvantages. The MLCs are constantly moving. There is more chance of MLC failure and more frequent maintenance required because they are constantly moving during the treatment. There's a higher contribution of leakage dose to the patient compared to step and shoot. You can use jaw tracking to reduce the contribution of leakage to the patient. So with jaw tracking, the jaws will position themselves to the minimum field size at all times, accounting for the MLC position. So the minimum possible field size that the jaws can shape without getting in the way of the MLCs. Errors in MLC lead speed and acceleration can affect treatment a lot more. The complexity of this treatment technique makes it impossible to plan forward treatments. I don't know of anyone that could claim that they could plan this forwardly. Dose distribution is more sensitive to MLC leaf position accuracy and the effective of the rounded leaf ends than step and shoot and non-IMRT techniques. So it's much more sensitive to MLC leaf position accuracy because of the dynamic nature. Volumetric modulated arc therapy, or VMAT. It's a form of IMRT where the gantry angle, the MLC positions, and the dose rate are constantly changing to deliver the most effective dose distribution to the patient. So this is an example of a VMAT field I have here from the Eclipse treatment planning system. So you see the gantry is moving, and you have all the MLCs moving around the PTV. in order to deliver that dose distribution. So in a VMAT delivery, the plan is optimized by the TPS by a series of discrete gantry angles or control points. And then the MLCs just move between these field shapes at each control point. Now, the field shapes at each control point are restricted by the finite MLC leaf speed. So you can't just have any field size at every control point. There is a restriction to how fast MLCs can move between fields. But the TPS often can struggle to find an optimal solution with these restrictions. So what they normally do is the TPS will optimize with a small number of samples. So for example, 6 samples around the gantry. With these small number of samples, the MLC leaf speed is enough that it can pick any field shape at these six samples. And then you optimize those fields, find the best field size at those 6 positions, and then you add new samples between those, interpolate, and then re-optimize. So you can have fine-tune it, and then you keep adding up more samples, and you get the most effective dose distribution, most effective MLC leaf positions for that VMAT delivery. So the advantages of VMAT compared to the other techniques is that it's much more efficient treatment. So it often has shorter time than the other methods, and shorter MU per grade compared to the other IMRT methods. And because it has less MU per grade, it has less leakage contribution compared to the other IMRT methods. And you can get a much more conformal dose distribution to the planning target volume compared to other methods as well. And one other advantage that I forgot to mention here is that our planners in our department, our radiation therapists, actually find it a lot easier to plan these treatments. So it doesn't require as much expertise. They can just add 2 arcs, put their dose constraints in, and then just run the optimizer, and then go have a cup of tea, come back, and then it's done for them. Whereas for IMRT techniques, they have to decide what gantry angles are the best and optimum, and what collimator angles should they use. So the planners find it a lot easier to plan VMAT treatments than other treatments. Disadvantages: the gantry and the MLCs are constantly moving. Impossible to forward plan, and it also has the longest planning time due to long optimization requirements. So sometimes it can take 15 minutes, sometimes it can take 30 minutes just to optimize one plan. We've just recently installed Eclipse 16.1, which typically you can get an optimization done in about 5 minutes. Sometimes it can go up to 10 minutes, but it's a lot faster than it used to be. So it's a lot more, we can get a lot more patients through this way. And another disadvantage is you have a low dose bath delivered to the entire patient volume. So typically you have most of the patient is irradiated by the 10% isodose, whereas in other IMRT techniques they aren't. So for example, I've got some dose distributions here. I've got, this is the same test patient we have in our treatment planning system, a 5-field dynamic MLC, 7-field dynamic MLC, and a VMAT treatment. And if you see the 100, 95, and 90% isodose, you see they kind of bulge out a little bit for the IMRT, whereas for the VMAT, they're very conformal. And then the 50% isodose is the highest for the 5-field IMRT. It gets lower as you add more fields. And then for the VMAT, it is the smallest, so it is much more conformal. But then if you look at the 20 and the 10% isodose, the VMAT plan, the entire patient, in this region anyway, is getting irradiated by that 10% isodose, whereas a lot of the patients not being irradiated here. And then 20% isodose is covering quite a lot of the patients as well for this test plan anyway. So it's a lot harder to reduce the dose in VMAT plans. You can increase your optimization parameters to try and reduce, for example, dose to critical organs. So if you want to reduce your radiation here, you can add avoidance sectors or just increase your optimization objectives to reduce the isodose down this end. So it is possible to play with that isodose distribution, but you will still get a higher dose path to the patient compared to these other treatment techniques. Treatment planning. So the treatment planning, you set the beam geometry. The planner will set the beam geometry, so the gantry and collimator angles, and then they'll create a set of objectives. So this is the objective window in the Eclipse treatment planning system. So they set some dose volume statistics they want to achieve and a set of priorities to those dose volume statistics. And then the planning system will then perform an inverse optimization to try and get the best fluence to obtain those plan objectives. There are multiple different methods of optimization. So analytical optimization is similar to a reverse CT. So for a CT, so basically you get your dose distribution that you want in the patient, and then you do an inverse back projection back to the beam position to try and get a fluence map to get that dose distribution within the patient. And the second method is iterative optimization. So the set of objectives are used to create a cost function, which quantitatively represents the quality of the plan. So the deviation of the current iteration to the desired plan goals. And the planning system will iteratively modify the fluence in order to minimize the cost function. However, because you have so many objectives, the cost function may exhibit a lot of local minima. And to avoid getting trapped in these local minima and to try and find the global minima, an optimization process called simulated annealing is used. So in this process, the earlier you are in the optimization process, the more likely the plan will accept a higher cost function for the next iteration, rather than rejecting higher cost functions. And then the further along the optimization process you get, the less likely it will accept a higher cost function, because the more likely it is coming towards that global minima rather than the local minima. Yeah, so that's how this optimization process works. So now I'm going to talk a bit about commissioning and QA of IMRT. So the commissioning and QA depends on the IMRT system implemented, and the ultimate goal is to ensure that the treatment of a patient is delivered accurately and safely. So the key considerations, you need to consider what are the machine capabilities, what are the patient workload, what techniques and treatment sites do we intend to use or implement, and then what are the TPS requirements for planning data in order to plan these treatments. And you should also consider what are the machine limitations and what are the treatment planning system limitations as well. Key references for commissioning are APM TG142 and TG198, the new TG document, and APM TG119. And if you want to look at the TPS as well, TRS 430, and there are some other APM documents about TPS commissioning, which are also important for IMRT. So safety considerations, specifically for IMRT and VMAT, the main ones you want to consider is, does the bunker actually account for the IMRT and VMAT patients? So these are your shielding calculations, NCRP 151, because you have higher MU per gray for IMRT and VMAT patients, and therefore you have a higher leakage workload. And if that wasn't accounted for in your original calculations, then you need to reassess your bunker for IMRT and VMAT. You also need to ensure that the MLC complies with the IEC standards for electrical, mechanical, and radiation safety. So these are IEC 60601-2-1. Mechanical tests. So MLC position reproducibility. This is normally done at acceptance testing with the variant engineer. And this is an example on the right here. I've got, this is the field that Varian uses for acceptance testing for a Varian TrueBeam Linac. And all they do is they just use the light field, project this onto graph paper. We just test that the positions line up with the lines on the graph paper. Then they'll move the MLCs out and then move it back. We just check it again. Leaf position accuracy. So the easiest way to do this test is just to do a picket fence at each cardinal gantry angle. So you have multiple MLC leaves positioned to create one picket, and then you move them, create a second picket, a third picket, a fourth picket. So this is an example of the test that we use for our department, where we have the graticule inserted, and we analyze this using PITSPro, which is a analysis software, a commercial software that can analyze these type of images and calculate your leaf positions. MLC leaf speed. So in our department, we use the Ling test, which I'll talk about a bit later. But a very simple test you can use to test if MLC leaf speed effects are present. you can just use a sliding window plan. So this is where the MLCs just sweep from one side to the other with a small MLC gap. Measure that with an ion chamber and just modify the dose rate to force the MLCs to move faster or slower, and then just compare the dose you measure, and it should always be the same if you don't have any effects of MLC leaf speed affecting your dose. And then obviously your light radiation coincidence is another important test. And your MLC spoke shot or radiation isocenter. This is just when you rotate the collimator and deliver a series of thin MLC defined fields, and just compare and just check the center of all these lines line up in the center there. So dosimetry tests. So MLC transmission is an important test. So this contributes both interleaf and intraleaf. So the most simple method to measure the average transmission is to just use an ion chamber, and you can place it at different positions in a closed MLC field, take the ratio of this to the open field measurement, and this is your MLC transmission factor. More comprehensive method, you can use film. So this is an example of an image that we use for PIPSPRO. So PIPSPRO is an automated software that can analyze these films, and it will measure, and this is the test field you use for it. It'll measure the ratio of your MLC interleaf and intraleaf transmission, as well as your interbank transmission factor. And you can also use a scanning software. So when we commissioned one of our LINACs, what we did is we acquired these scans. So we just normalized, we set up our water phantom as we did for the rest of our commissioning tests. We placed the ion chamber at 10 centimeters deep with 90 centimeters SSD, a 10 by 10 field. We normalized our chamber to that, and then we closed the MLCs and just did a scan with the scanning software, and you get these nice profiles. And you see the highest leakage is 2.5% for the 10 MV, and the average leakage is less than 2% here. So that's just a fancy way you could test that. And then you want to test your tongue and groove effect. So the easiest way to do this is just scan. You can scan a 10 by 10 field with an MLC defined field in the direction perpendicular to MLC leads, and you just look at the effect that it has on the penumbra. Another method that people can use is you can use a comb pattern of MLCs. So you have half the MLCs closed, the other half open, deliver a field, and then swap the MLCs. So the ones that were open, you can close them now, and you open up the other MLCs, and then you just look at the peaks between the MLC leads. So there'll be slight peaks between the MLC leads, and that corresponds to the tongue and groove effect. So the dosimetric leaf gap, this is required by the Eclipse treatment planning system, and it's a method to model the rounded MLC leaf tips. So the rounded MLC leaf tips cause an increase in the transmission through the leads, and this creates an effect that it widens the penumbra and causes an apparent increase in the field size. And this most impacts dynamic MLC and VMAT treatments, not as much for step and shoot treatments, but it does impact it a little bit. And it is modeled in the Eclipse treatment planning system as an offset in the MLC banks by half of the DLG. So we offset each, so it essentially offsets each bank by half of the DLG when it models the MLCs. So the method of measuring the DLG is you set an ion chamber at 10 centimeters depth in water or solid water, measure the MLC transmission, RT, take ion chamber readings for multiple different gap sizes. So what you do is you deliver sliding window gap plans where the MLCs slide from one side to the other, delivering the same number of MUs with multiple MLC gap widths. So for example, we go from 20 to 2 millimeter gap widths between the MLC banks, deliver those to an ion chamber. Then we correct those readings for MLC transmission using this formula here. And then we plot the results against the gap width, and then the x-intercept is the DLG. So if we extrapolate back here, you can consider it that this x-intercept is the amount of overgap you require in your amount of overlap you require in your MLCs to reduce the interbank transmission to zero, essentially. So this is your gap width, your DLG, and this is what you input into your treatment planning system. So in our department, we also measure sliding gap with gantry angle. So we have a 6mm gap, sliding gap that we measure at each gantry angle, and we test that routinely on a 6-month basis. And that just ensures the constancy of a DLG, and our dynamic MLC treatments. We also do Ling tests. So these are recommended from Varian to do rapid arc commissioning. And this is from this paper down here. So there are 3 different tests. There's a T1 test, which tests for MLC leaf positions during VMAT. T2 test tests for gantry speed and dose rate during VMAT delivery, and T3 test for MLC leaf speed during VMAT delivery. So these are some example images, and these are taken from the analysis software we use. It's an in-house software we made. And this is the Ling test. So Ling test open field, what it does is it takes the ratio of the dose at each of these points to the open field ratio dose. Does that for every single one of these boxes here, and then it will compare all of those ratios that are calculated to the mean ratio, and they should all be the same, if these parameters are correct. So if for example, for the T3 test, if the MLC leaf speed doesn't affect the delivery, then these ratios should all be the same. Whereas if the ratios were not the same, then there'll be impact of MLC leaf speed. And what I should say is that for the T3 test, for example, the dose rate is changed, but the MLC leaf speed is changed for each of these pickets, and then they just keep the same, they just modify the dose rate in order to account for that. So these should all be the same intensity if there was no impact of the MLC leaf speed. So that's what the Ling test does. And then you should also measure PDD's profiles and output factors for treatment planning. Some TPS use jaw data. I know the Eclipse treatment planning system that we use requires jaw-defined data for your beam modeling, but you should also measure MLC data just to compare to the TPS to ensure the TPS accurately models the MLCs. And importance for IMRT and VMAT is you need to do your small field measurements, because during IMRT delivery, you can get a lot of small segments. So your small field model is important in your IMRT and VMAT delivery, as well as your SBRT treatments as well. Modeling of the MLCs and the TPS. So in Eclipse treatment planning system, it requires the average MLC transmission and the DLG in order to model the MLCs, in addition to the jaw-defined data, which it uses to create the beam model. But then you can also modify the source size to improve the model, to improve mainly the penumbra if you want to. And then you have to validate the model. So the simple basic test is to compare TPS calculated MLC defined PDD's profiles and output factors to the measured data. More complicated tests we use, in our department, we use MLC defined test fields. So these are just examples of the test fields we use. So we have a mock head and neck, we call this 7 segments, so it has 7 MLC defined fields. This one has 4 L-shaped fields, and then we have this dynamic MLC chair shape pattern. And these are just what we do on all our Linux, just to check that our MLC delivery, our step and shoot, and our dynamic MLC delivery are working correctly, and that our TPS model is valid for our machine. And then we also do AFBM TG119 tests. So these are a set of different plans used to test your IMRT and VMAT planning and delivery methods on your machine, and that they are accurate. So this is an example of the C-shape plan, where you have this PTV with a organ at risk in the center, and this is one of the most difficult plans to achieve, and it basically pushes your treatment planning system and your machine to its limits to see how well your machine actually is. And then this is another example of the TG119 tests. This is the mock prostate plan, so it's just a simulated prostate plan in solid water. Other tasks for commissioning, once you've done all that, you want to look at some patient plans. So depending on what treatment techniques and treatment sites you're using, you want to consider the patient-specific QA method, and you'll have to commission that if it's a new, especially if it's a new department, or if you're doing something different. Develop your planning protocols, treatment and QA protocols. You want to do end-to-end testing, develop your QA program. In Australia, we need to do a level 3 audit, and I'll quickly talk about that. And then training and commissioning report are all important facts for the implementing IMRT and VMAT. So just quickly, independent audit is a legislative requirement in Australia, and we need to do it for all planning delivery techniques, so all new machine installations, all new treatment sites or treatment techniques that we want to implement. And it's essentially an end-to-end test, but the independent body performs the measurements using their own calibrated equipment that is not traceable to what we're using. So completely independent calibrations between our equipment. So often we always get a local centre, so to do it that has no affiliation with our own, for example, Genesis, Cancer or Icon. So they're two different independent centres that are close by, and we also do audits for them as well. And then we get ACDS, which is the Australian body, and they have to do an audit for us as well. So we normally get an independent centre to do it, and then we get ACDS to do it after they've done it. And essentially just an end-to-end test. So phantom is scanned and treatment planned by the RTs. Patient-specific QA performed. Plans are sent to the independent body with a set of planned point doses. And then on the day of the audit, the RT, so the radiation therapist, will set up the plan using IGRT methods and then deliver the plan. And then the independent body will just position their calibrated ion chambers or film in the phantom to measure the dose and compare to the planned values. And then they'll send us a report to say whether it passed or failed the audit. QA, so these are recommended QA form AAPM TG 142 on MLC QA. Weekly or qualitative tests are just, for example, just a picket fence. Monthly, you have MLC leaf positions for electrolytic backup diaphragm, MLC travel speed and leaf position accuracy. Annually, you want to test your MLC transmission, leaf position repeatability, spoke shot tests, light radiation coincidence, and then you want to do a step and shoot test and a moving window test. We also do a VMAT test as well, just a simple test plan that we deliver to make sure everything's working properly. Okay, patient-specific QA. So all IMRT and VMAT plans should undergo patient-specific QA. It's an independent verification of the planned patient treatment. It involves measurement and verification of the delivered doses prior to patient treatment commencing. The goal is essentially to ensure the deliverability and accuracy of the treatment plan compared to what you, AAPM TG 218 provide recommendations for performing patient-specific QA. So I'm going to go for a bit of what AAPM TG 218 now. So ion chambers is the most basic method of performing verification. Place an ion chamber in the center of your PTV in a phantom, deliver the radiation treatment, and then measure the dose. It's very good absolute dose determination. Has much less uncertainty than other measurement devices, but the disadvantage is it's just a single point, and because it's just a single point, it does not provide enough information to validate plan accuracy for IMRT and VMAT plans. Second form of detectors is array detectors. So array detectors have much more measurement points. They're often diodes or ion chambers. You can have liquid or gas-filled ion chambers. There is a sensitivity variation between detectors, and these are normally corrected for through array calibrations. And then vendor software also incorporate algorithms to correct for angular dependence and field size dependence on individual detectors. So examples of these, I've got the Octavius, PW Octavius, SNC ArcCheck and SNC MapCheck. So these are all examples of array detectors that you can use for patient-specific QA. Advantages that these have much more measurement points and they provide instant readout. Disadvantages is that they're less accurate absolute dose determination than an ion chamber measurement. There is limitations on resolution, and not all the treatment beams pass through the detector array. So sometimes, so the ArcCheck can reduce this issue, but for example, MapCheck, not all beams will pass through the array when you deliver the treatment. Film, so film has the advantage that it has a high resolution, especially for small fields such as SBRT. but you have a delayed readout, and it can have more uncertainties than other methods and requires more dedicated staff time per patient to deliver these fields. Portal images. So the advantage of portal images are normally attached to the LINAC. So most modern linear accelerators have a portal imager perpendicular to the main treatment beam. Allows for automatic setup. The RTs can easily perform imaging daily before and between patient treatments. So in our department, we use portal dosimetry, and in the morning after the RTs have done the daily LINAC QA, they'll deliver maybe 3 to 5 portal dosimetry plans for every machine. And that is a lot faster than us trying to set up the ARC check at 5 o'clock at night and trying to deliver 5 or 6 patients. Because of this, it's less staff time per patient, allowing higher patient throughput, and implementing portal dosimetry in our department has allowed us to increase our percentage of IMRT and VMAT plans significantly compared to when we had the ARC check phantom. And it does have a high resolution as well. Disadvantage is that it's a perpendicular technique, and I'll talk about those in a minute, and you can ensure errors caused by gantry rotation. So these are some different delivery techniques defined by TG218. So we have a true composite with a planar array where the detector is placed in a solid water phantom with a cylindrical array such as an ARC check. And for these, you just set up the phantom, align it, and then you deliver the treatment and measure it. And you have a composite analysis. Then perpendicular composite and perpendicular field by field technique. So these is when the beam is always perpendicular to your array. So if you override all the gantry angles and place your array detector here, this is a perpendicular technique. If you deliver it field by field, then it's perpendicular field by field. If you deliver it all at once, it's a perpendicular composite. And same with the EBIT panel, that's a perpendicular technique. And TG218 says that using the EPID to obtain an integrated image for a VMAT arc is considered a perpendicular composite, not a perpendicular field by field. So advantages and disadvantages of each. So true composite includes inaccuracy of the gantry, collimator, couch, MLC positions, couch attenuation, the dose distribution closely related to that within the patient, and only one image is to analyze per plane of image. The disadvantage is that many portions of the beam may not transverse the detector plane. Perpendicular field by field, this prevents the dose washout that can occur during composite measurements. For example, if you have a point where one field is delivering a lower dose, whereas the other field is delivering a higher dose, and these will average out and it will result, and you won't be able to see that error. Whereas in a field by field technique, you will see that error. But the comparison is more dependent on the normalization point than a composite measurement. So you can change the normalization point for each field and get a better result than a true composite, and that might not represent the actual result that you want to look for. Perpendicular composite technique. This is a single image, simple setup, and can be quicker than other methods, but it can mask a lot of dose delivery errors. You get a dose washout effect due to summation. It can obscure dose rate variation with gantry and VMAT. It can't detect gantry errors, and errors from uniform versus non-uniform dose rate deliveries are hidden. And TG218 recommend not performing this type of method, so not performing perpendicular composite methods for IMRT QA. So analysis methods, I'll try to quickly go through this because I'm running out of time. Dose difference is a one-to-one comparison of difference in dose between measured and calculated. It's a good comparison in low dose gradient region, but fails in high dose gradient region. So for example, if we have a dose distribution here, a dose difference result will have something like this, where the failure points occur in the field edges. Distance to agreement is the distance between a point in the calculated distribution that has the same dose in the measured distribution. So it's a good comparison in high dose gradient region, but it fails in a high dose. So it fails in a low dose gradient region, sorry, not a high dose. That's a mistake in the slide. So for example, if we take this distribution, it will fail most places except in the gradient region there. A composite analysis is essentially if a point passes dose difference, or if a point passes TTA.
We have a question here.
Yes.
So in VMAT planning, is the collimator angle reduce the MLC leakage? If yes, then how?
So collimator angle, it won't
Yeah.
necessarily reduce MLC leakage, but what it will do is it will make the MLC leakage contribute differently to different parts of the patient. So it will essentially, so if you place, you have a 0 degree collimator angle, then the intervein leakage will all be affecting in the same region, so the same plane of the patient. Whereas if you rotate your collimator angle, then it'll basically spread it out towards all the patients. So you'll have less contribution of leakage to each point, but if you have a 0 degree angle, then you'll have the leakage will basically be contributing to the same points. Essentially, does that make sense?
Yeah, I think that would answer the question. There's
yeah.
one more question here.
Yep.
So did any QA after any maintenance replacement service of the MLC recommended?
Yes. So in our department, when we replace an MLC motor, which happens quite often, we just do MPC again. So machine performance check is a variant module that tests a lot of different things, including MLC leaf positions. And we did validate that for about 3 or 4 months, where every time we did machine performance check, we did a big offense test and a light radiation coincidence test as well with the MLCs. And over a few months, we decided that the machine performance check was a good enough result for us to say that the MLCs are good enough to use. So if the MLCs are replaced, we just do that test and then we release it clinically. Yeah.
Okay, thank you. And one more question: how VMAT reduce the MU per gray compared to IMRT?
So this is a bit of a hard question to answer. I'm not actually sure the answer to that, but I definitely do see it in our patients that we always have a lower MU for VMAT plans compared to IMRT for the similar dose. So I think it's more that most likely the reason is because the MLCs are more open during a VMAT plan compared to the MLC plan where you have a lot more, DMLC plan where you have a lot more closed segments compared to the open segments you see in VMAT plans. That's what I think it is, but I'm not 100% sure about what the cause for that is.
Okay, thanks.
So I'll continue. So composite analysis, if it passes dose difference or DTA, then it passes. If you combine these two results, you get a good result in your thing. The problem is that we cannot quantify by how much a point passes or fails. And that's where gamma analysis comes in. So gamma analysis is where you create an n+1 dimensional space of dose and position. So for example, a 1D array becomes a 2D space. Then you rescale the axis by dividing the dose and the DTA criteria. And then you calculate the distance between the evaluated point or the measurement point and each point in the reference distribution in the renormalized space. And then the minimum distance is your gamma value for that measurement point. And if the gamma value is less than 1, then the point passes. If it's greater than 1, then the point fails. And you repeat this for all points in the measurement distribution, and the number of points that pass to the total number of points is your gamma pass rate. And the advantage of gamma analysis is that it's good in both high and low dose gradient regions. So in a high dose gradient region, your gamma is very similar to your DTA. And in a low dose gradient region, your gamma is very similar to your dose difference. So the recommended analysis method is a 3% 2 mm gamma analysis using tighter criteria for SRS SBRT, 10% threshold, and a global analysis. And they recommend reporting gamma pass rate should be greater than 95%, maximum gamma less than 1.5, and to reduce, they recommend reviewing the dose distribution and any locations of failing points if the gamma is less than 100%. So even if it's greater than the 95%, they still recommend to have a look at where those points are failing and see if there are any significant points. In our department, We do portal dosimetry for all patients, 95% tolerance with 3% 2 mil global gamma analysis, 10% dose threshold. So this is in line with TG218. If the plan fails, then we'll do a per field ARC-check QA for all patients. For SBRT, we use a 3% 1 millimeter gamma analysis for portal dosimetry, and we'll also do a composite analysis with film in a cylindrical phantom with a 3% 1 millimeter global gamma analysis as well. We also do a point dose measurement, but we are slowly going to be removing that requirement as well for SBRT. So we do a lot of QA for SBRT patients at the moment. All right, so the second part of my presentation is on IGRT. So this is a bit shorter than the rest of the presentation, so hopefully I'll have enough time. So IGRT is broadly defined as a radiation therapy procedure. Yep.
Can I have a comment? Thanks, Luke, for your presentation. Just a quick comment about how to reduce the, because Luke is my colleague and you work in the same department. Okay. If in VMAT, ASC is the way, one way is to how to reduce your MU per grade by choosing a higher, you know, this aperture. Yeah.
Shape controller.
Yeah, by increasing to high, you reduce the MUs. By you going to low, it will increase the MUs because it will use more
higher modulation.
So just to thanks a lot.
Thanks, Ed. All right. So IGRT can broadly be defined as radiation therapy procedure that uses image guidance at various stages of the radiotherapy process. But in the modern context, we use this term to describe radiotherapy that uses image guidance procedure for target localization before and during treatment. So the goal is to reduce both systematic and random errors in patient treatment, allowing reduced PTV margins. So the ideal system must be able to relate images created to the beam geometry, provide adequate soft tissue contrast for target localization, be fast and simple to not considerably affect patient treatment time, be accurate within the limits of target definition, give minimal extra dose to the patient, and give information about treatment offsets in multiple dimensions. So the two different protocols of IGRT. Offline protocol, I don't see this used much anymore. So basically, we don't use it in our department at all. The image, the patient before and or after treatment, you review the image at a later date, and then you correct for systematic uncertainties for future fractions or for a patient group, so multiple patients. And this can be used to reduce systematic uncertainties. Then an online protocol is where you image the patient before treatment, you match the image to the reference image. So you do your image matching online, then you correct the setup before you treat the patient. And this reduces both systematic and random uncertainties in your treatment setup. So image registration is the process of relating the anatomy of one image to another through a transformation matrix. And in IGRT, this transformation matrix represents the optimum shift in the treatment couch to correct for any positional errors of the patient. Most Linacs do have an automatic image matching software, but the RTs always manually adjust the image after the automatic registration just to correct for any, just to ensure that the machine is actually operating correctly, and they'll do the manual match themselves. Image fusion is when multiple images are displayed together, and this is done to assist in aligning and verifying the correct registration of image. AAPM TG132 is a recent document that provides information on commissioning image registration and fusion algorithms, both on the Linac and in the treatment planning system. So this is talking about rigid registration. There's also deformable registration, which is more used for adaptive planning, and more modern systems are available now that can do adaptive planning with deformable registration. So reference images for your image matching. Nowadays we have digital reconstructed radiographs or DRRs for planar imaging setup, and you can use different algorithms in your treatment planning system. So this basically uses the planning CT, and it will ray trace a KV beam through that planning CT using the setup geometry to create an image like this. And you can use different algorithms to enhance different aspects of the patient for your image matching procedures. And then the other option, you can use a planning CT, which you use for cone beam CT setup on the Linac. So some IGRT systems. So portal images are a 2D megavoltage X-ray detector positioned perpendicular to the main clinical beam, and all modern linear accelerators now are equipped with a portal imager. So this is a quick little diagram of it. You have a copper plate. This provides buildup of secondary electrons, a phosphor scintillation crystal. This converts your secondary electrons to scintillation light photons. You have amorphous silicon photodiodes, which convert those light photons into electrical signal, and then this is output to your image, and you apply certain corrections to get your image. The advantage is a direct relation to treatment geometry because you're using the main clinical beam, and it's good for bony anatomy and fiducial markers. Disadvantage, you have a high patient dose compared to KV imaging, so much higher dose. Poorer image quality than KV imaging, and this is because the Compton scattering, lower soft tissue contrast than KV imaging because it primarily interaction is the Compton effect, which is less sensitive to patient density than the KV imaging is, which uses the photoelectric effect. The onboard imaging system. So this is a gantry mounted KV source and detector, and again, most modern systems have this on them. So the OBI is orthogonal to the main treatment beam. So if you see the variant true beam here, you have the KV source, KV detector, and this is the Electa Versa HD, KV source, KV detector is orthogonal to the main treatment beam in both these systems. The OBI is capable of planar KV imaging, fluoroscopic imaging, and KV cone beam computer tomography, or CBCT. For these systems, because it's not using the main clinical beam, the alignment of the KV isocenter and the treatment isocenter is critical for accurate setup corrections. So KV CBCT, planar projection images are acquired at multiple different gantry angles as the gantry is rotated, and then it reconstructs as a 3D volumetric image using filtered back projection. But it has to apply multiple corrections. So first it has to correct for positional inaccuracies in the source and detector arm. And this is corrected at each angle using an image flex map that is taken at commissioning and recalibrate at regular intervals. So we recalibrate it every 6 months, and we do a isocenter calibration, and this just corrects for the inaccuracies in the position of the source and arm compared to the megavoltage isocenter. The problem with using a cone beam rather than a fan beam CT is that it increases the lateral scatter, and this increases noise and reduces spatial and contrast resolution compared to a conventional CT scanner. And there are correction algorithms that are used to reduce this. So iterative CBCT can reduce the effect of noise and increase the spatial and contrast resolution. And there are also correction algorithms used to reduce effects of artifacts such as beam hardening and scatter artifacts. And the result is a 3D image with very good soft tissue contrast and sub-millimeter resolution. And registration with the planning CT allows corrections at 6 degrees of freedom, and you can also use registration to soft tissues such as the prostate or bladder, for example. Just to show you the difference in noise, so the KV CBCT, this is a cat fan on the left and on the right for a KV CBCT and a CT. So you see there's a lot higher noise in the CBCT compared to the CT because of that cone beam. Megavoltage CBCT, so this uses the MV beam and the portal imager. The main treatment beam can be used, and the advantages are that because it's using the main treatment beam, you don't have to worry about the KV-MV isocenter difference, and it is less susceptible to artifacts from metallic objects. It's more accurate in calculating image dose because using the main therapy beam, you can just use the planning system to estimate the dose of the patient from your imaging. And it doesn't require a separate imaging system on the machine. Disadvantages is you get a lot lower contrast and spatial resolution, a lot less visualization of soft tissues, and much higher imaging dose compared to KV CBCT. Room mounted systems. So These are mainly used for stereotactic treatments. So you have two KV source and detectors mounted on the ceiling and floor. So if you have the ExactTrack system, you have the KV source on the floor and the detectors in the ceiling. And on the CyberKnife, you have the KV source on the ceiling and the detectors in the floor. So these used to at a large number of gantry and couch. So these can be used at a large number of gantry and couch angles, whereas the onboard imager, you are restricted by your couch angles because the true beam will hit the couch if you're trying to do a cone-in CT at couch 90 or 270. And this system, because they are both orthogonal to each other, you can estimate offsets in 6 degrees of freedom. And especially with the CyberKnife system, you can allow you can take images multiple times during the treatment and correct setup as you are treating the patient. And that's what the CyberKnife does. I'm not a huge expert on ExactTrack. Forgive me that they might do that as well. I'm not sure. In-room CT. So this is where a conventional CT scanner is on rails, and it shares the same couch as the LINAC. The couch is rotated in line with the CT scanner for pre-treatment imaging and then rotated back to and aligned to the LINAC for treatment. And the image quality is comparable to the planning CT. The only issue is you need to have more mechanical accuracy in your couch, and you have to ensure that the imaging isocenter of the CT matches the treatment isocenter of the LINAC when you do this. MRIs, so there's a lot more advances in the MR LINAC. So they combine an MRI imager with a short linear accelerator. Examples of the Electra Unity and ViewRay MR IDM. The advantages of MRI, it offers superior soft tissue contrast, no imaging dose, and these systems are designed for adaptive planning and for tumor tracking. So they're designed to do deformable image registration after you image, adapt the plan, and then treat the patient, and it can also track the tumor during treatment as well. So it's very fancy technology. Respiratory motion management. This is a very important part of treatment because respiratory motion affects all tumor sites in the thorax, abdomen, and pelvis, such as lung, liver, pancreas, esophagus, and breast. Especially lung tumors that have been shown to move several centimeters during respiratory motion. So if you don't account for that motion, you can miss the tumor for part of the patient treatment, or if you do account for that motion, you can actually irradiate a lot more of the patient, which is one method you can treat that tumor. So in an extreme case, so when imaging, the motion of the tumor does create motion artifacts, and in an extreme case, you can see here, so you see the tumor is moving this way at the most extremes, and at the most extreme case, they can sum together to create a large tumor that is larger than reality, or you can image the intersection and get just a tiny tumor. So this is why 40 CT imaging is important for, or using gating technology is important for imaging moving tumors. So 40 CT is a process of requiring CT scans of the patient at each phase of the patient's breathing cycle. Often you reconstruct 10 phases. For the variant system, which we have, the RPM system, each projection of the CT scan is correlated with a phase of the patient's breathing cycle. And then the scanner will then use this RPM signal to assign each projection image to a different bin, and then reconstruct 10 phases based on those images. So this is an example of a max inhale and a max exhale phase. And then this is an example of a 40 CT scan. So you see those 4 phases of the patient breathing with that 40 CT. So it's good to see tumor motion in the lungs and also the abdominal region. Gated treatment. So for gated treatment, the beam is switched on only during the desired phase of the patient breathing cycle. And we track that respiratory motion using, normally using the height of the patient's surface. So in our department, we use the variant RPM box, and it contains some infrared tracking markers that are placed on the patient's abdomen or chest and tracked with the RPM system. For breath hold, so we have, so for breath hold and so deep inspiration breath hold and exhale breath hold techniques. We scan the patient with that breath hold, and then we will plan the treatment with that breath hold, and then we'll deliver it that way. So for example, this is a patient breathing trace where they're breathing normally, and then they deep breathe in and then hold their breath, and the treatment will commence here. And if they accidentally breathe out in the middle or cough or something, then the treatment will terminate. But we try to design the field so that it delivers in the amount of time the patient can hold their breath for. And then we have these little screens in the room to help the patient, to coach the patient in how to breathe in. So this little white bar will move up and down based on the patient breathing, and they try to get into this green zone to treat. Real-time tumor tracking is another method of respiratory motion management. The goal is to detect the motion of the target and reposition the radiation beam in order to follow the tumor motion during treatment. For example, the Slama system does this. This can reduce random uncertainties due to respiratory motion during treatment. There's also so there's fluoroscopic systems such as ExactTrack and Cyberknife, electromagnetic field tracking such as the Calypso 4D localization system, and then MRI, so the new Electro Unity Linac and the ViewRay MRI Linac use MRI tumor tracking. Adaptive radiotherapy. So this is a radiotherapy process where the treatment is adapted to account for internal anatomic changes. It is critical for, IGRT is critical for adaptive radiotherapy. So there are multiple methods, each with increasing complexity. So the most simple method of adaptive radiotherapy is when the RTs notice that the patient has lost weight or the tumor has shrunk, or there's a difference in the CBCT compared to the planning CT when they do the image matching. And then all they do is they send the patient back to CT, replan the treatment, and then send them back to the treatment unit, and then they deliver for future fractions. So this can happen a lot for head and neck patients in our department anyway, where patients can have maybe one, maybe two replans during the course of their treatment. So it's the most basic form of adaptive radiotherapy. Plan of the day. So we have done it for bladder treatments in our center where the volume of the bladder can change significantly between fractions. And what we do is you create a library of treatment plans at the start of the radiotherapy based on different sizes of the bladder. And then on the day of treatment, you pick the plan that closely matches the size of the patient's bladder on that day using IGRT. So it's a way of adaptive radiotherapy where you can pick the best treatment plan for the day based on the library that you already have. And then the most advanced form is to perform the formal image registration on the day of treatment, replanning and re-optimizing the treatment plan for each fraction. And this is what they do for the MR Linac, where, so in Genesis Cancer Center, near us here, they have an MR Linac, and they, the ROs have to be on the machine for every patient to re-outline the patient, re-outline their PTV, and then re-optimize and replan the patient before delivering for each fraction. QA, so I'll quickly go through this. From AFM TG142, daily QA, you do collision interlocks, positioning. So this is for a, based on a Linac-based OBI and MV imager panel. So collision interlocks, positioning, repositioning. This is basically just the ability to move the couch based on image matching, image and treatment coordinate coincidence, or KV MVI center coincidence. For chromium CT, you do collision interlocks. They're basically the same tests as the planar KV. For monthly tests, you want to do obviously your imaging treatment coordinate coincidence, scaling, which is your distance measurement, spatial resolution, contrast, uniformity, and noise. You do that for all the MV, KV, and chromium CT imaging. In addition to chromium CT, you also do your HQ constancy. And then annual QA, you want to do your mechanical positioning of the MV panel, so the full range of travel SSD, and then you want to do your imaging dose, beam quality or energy for KV imaging, and then your imaging dose, and CBCT, your imaging dose. So that's it for my presentation. Thank you. Is there any questions?
Thank you very much, Luke. I encourage all the participants, if you have any question, please unmute yourself and ask the question.
No questions?
I think there are no more questions. Thank you very much, Luke, Salma.
Thank you for inviting me.
Thank you. On the behalf of Medical Physics Foundation, I would like to thank all the speakers before you, and we will like to see you again on our next or upcoming webinars. Thank you very much for sparing time and participating in the Radiation Therapy Week to honor Faz Khan. Thank you very much.
Thank you.
Can I have a question?
Yeah, you can, please.
Yeah, this is Kapis calling from Kenya. So my question is on portal dosimetry.
Yep.
Sometimes we do portal dosimetry and we realize that the composite image fails while the individual field passes the gamma criteria. What do you think is causing this?
So when
The other question, the other question is about the normalization mode that we should be using. Most of the time I use the absolute, but if you are to apply the relative, where the relative you also have a lot of options. For example, you can have the normalization at the maximum. It could be the maximum of the selected, selected point dose, or at the ISO center, or the minimum difference. They all give different results. So I don't know.
Yeah, so
whether you would have.
It's very sensitive to normalization. So what we do with portal dosimetry, we'll always do absolute dose, just because you can play around and get different results with different normalizations. In terms of composite and per field, I'm not sure what's causing that. Normally what we see is that a composite will normally pass when a per field will fail. So I'm not sure why that's the case for you. I'm not 100% sure for that. But yeah, I would recommend, and TG218 recommends using absolute mode where possible as well. Does that answer the question?
Yeah, I think I still remain doubtful, but I'll still have to investigate. Now, one other thing that I've also noted with the portal dosimetry is that for some plans where the normalization was very tight, you have to use a very high priority to get your objectives, you'll find that most of the time the portal dosimetry fails. I don't know, but the relaxed plans, the ones that were not very tight during the normalization, you find that they pass at a very high gamma criteria, like over 98%. What is causing it?
So you mean when, what do you mean by tight? When you select a normalization point, is that what you're talking about? That sometimes it passes?
Yes, what I mean is that there are certain plans, for example, head and neck, you really want to get certain objectives and you are to use very high priority to get the objective, either for the constraint, but some plans where the organs at rest are far away, so they are kind of relaxed. You're not using a lot of priority to get your optimization.
So what I understand is that the, especially for Eclipse, that the, so for VMAT, the aperture shape controller, and for IMRT, your fluent smoothing, those are also considered an objective, and they have an associated priority to them. So if you optimize your treatment plan with huge priorities to your organs at risk and to your PTV, they will actually outweigh the priority to your smoothing. And what you'll get is you get a much higher modulation in your MLC fields. You get a lot more smaller segments. And in that case, the portal dosimetry algorithm might not be very good. And also your treatment delivery might not be as good compared to your treatment planning system. So a much higher, if you're trying to push your optimizer too much with higher priorities, it could actually make portal dosimetry fail because of that priority to smoothing that impacts that. Does that make sense?
Yes, I get what you say. But do you think the portal dosimetry help us in getting the dose to go into the patient, or it is the leaf modulation that is what is being compared?
So portal dosimetry is using the measured dose delivered to the EPID panel when you deliver the patient treatment. And that is affected by the MLC leaf modulation. So higher MLC leaf modulation means that there's more chance of the portal dosimetry failing. And you might also say the machine might struggle a bit more to try and get that higher modulated field. So whether it's the machine that's failing or whether it's portal dosimetry that's failing, it's difficult to say, but it could be a combination of both of those two that are the issue.
Okay, thank you.
Any more questions? Okay, so we have a question here. For Electa machines, are we use the calculate test for MLC, example, picket fence test, and compared with the measurements?
So we don't have Electa machines, we have Varian, and what we do is we just, for picket fence, we would just use, we use a PIPS Pro analysis, and that basically scans profiles and basically measures the full-width half maximum to calculate the MLC leaf position. For our MLC test fields, which we use, picket fence has multiple other test fields, we use a TPS calculated dose plane and do a gamma analysis compared to a film-based measurement. And that's for our test fields. So the chair shape pattern and the head and neck pattern I showed you earlier in the presentation.
Okay, so there's one more question. In IMRT treatment plan, if fields are not symmetric, for example, isocenter is close to one axis, then in patient-specific QA, when we set the isocenter on Octavius center, the field border farther from isocenter set outside the phantom. It means that the field is not fully covered the phantom. How can we overcome this problem?
Okay, I'm not an expert on the Octavius, but so you're saying that not all the field is being covered by the phantom. Yeah, I'm not an expert on the Octavius. I'm not sure if you can shift it or not. I don't think that's, I know for the arc check, you can't shift it laterally. So I'm not sure if the Octavius has that capability, but for the arc check, we just miss the beam. It's not really much you can do with that. And if it's long treatment field in the GT direction, you can actually shift and rotate the arc check and create a composite analysis. I'm not sure if the Octavius has that capability or not. I'm sorry, I can't answer that question.
Thank you. So no more questions. Thank you very much, Luke, for your time and participating in the Medical Physics Week for radiation therapy.
Thank you.
In honor to Fazkan. Thank you very much for this informative session. And at last, I would like to end with the thanks to all the participants who make this event successful. And I would like you to please send your suggestions and comments to info.mpt-foundation for how you think about this session and what would you like to see, because this MPT is an open forum. You can participate, as well as if you want to learn about a specific topic and want to listen any specific speaker, you